series is a white noise, what are you looking for?
Lag 0 to equal 1 autocorrelation, and all the other correlations for the consecutive lags equal to 0.
Exactly. That's it. Isn't that simple?
Well, don't you just start with a constant mean first?
Yeah. Mean, variance, we're assuming those are constant, okay? But what are you looking for in terms of autocorrelation? Everything else is 0. At other lags, everything else is 0. But at lag 0, the autocorrelation is +1. So if the mean is constant, it's a number constant, and the variance is a number constant and finite, and the autocorrelation at different lags are 0, then you can say it's a white noise. Okay.
Professor, so on a financial time series, we're testing to see if the asset has weak stationarity, and if it does, and we find that autocorrelation at lag 0 is 1, and all consecutive lags after that are equal to, lag 0, autocorrelation at lag 0 is equal to +1, and then all the consecutive lags after that are equal to 0, then we say that this is a white noise process?
Absolutely, yes.
Okay.
You think it's complicated? It's not. It's just simple. So I've just given you the conditions. So the money. So anytime you have a time series and you want to test if it's a white noise, the first thing you want to look at is autocorrelation function. If it's all zeros, then you can test other things. If it's not 0, then definitely it's not a white noise. Okay, guys? Okay. Now, what I want to explain now, I want to test your understanding of statistics and Echo 4000. And all of you understand this. Okay, so maybe you have forgotten or you're not really sure what I'm talking about, but let me explain this, okay? Okay. I want to make a statement now. Every student at Baruch College is at least 5 feet tall. Every student at Baruch College is at least 5 feet tall. Can somebody explain in English what I just said?
The expected height of all work students.
You're complicating it. Expected height.
Population?
Yes, so suppose I say every student at Baruch College is 5 feet tall or above.
Got it.
Okay, that's what I said, at least 5 feet tall. Okay. Now, so I come to Baruch College and I measure, I take somebody at random and I measure their height and I say, well, this person is 4 feet 9 inches. Therefore, every student at Baruch College is not 5 students. Then I'm correct. But if I say on average, that the average height of students at Baruch College is 5 feet. The average height of Baruch College students is 5 feet. Does that mean that if I come and take a random sample, that everybody in that sample has to be exactly 5 feet?
No.
No.
No. Is it possible that I can take a sample or some samples, and maybe in those samples, the average height is actually 7 feet, 6 feet 5, 6 feet, but still that my hypothesis is true, that the average height of Baruch College students is 5 feet. Is it true?
No.
Yes.
Yes, it can be true.
It will be true.
Depends
can
on
be
number
true.
of observations.
Yes, or maybe the 3 samples I took are the wrong samples. Is that right?
Oh, and that's
Yes.
the samples. Okay.
Okay, so yes, Lily, I know you misunderstood my question. So that's what we all studied in statistics and Echo 4000 and so on. Because, and what do we do in statistics in order to confirm my hypothesis, whether my hypothesis is true? Yeah, or my hypothesis is false. We do confidence interval and then we extend it to hypothesis testing, where we say null hypothesis is this, alternative hypothesis is this, so that even if I take a sample and the average height in that sample is not exactly 5 feet, it can be more than 5 feet or less than 5 feet, my hypothesis can still be true or can be false. Are you with me so far?
Yes.
Okay. So if I say the average height of Baruch College students is 5 feet, and I come and I take a sample, and for that sample of 30 students, the average height is 6 feet 2 inches. That doesn't mean that my statement is wrong. That the average height of students is 5 feet. Okay, that doesn't mean. If I say the average height of, hey, the average height of Baruch College students is 5 feet, and I immediately take a sample of 30 students and I measure, and the average height in that sample is not 5 feet, it doesn't mean my statement is wrong. That's why you do confidence intervals. That's why you do hypothesis tests. All right. Hold on, everybody. Let me make this statement. I give you a time series, and you measure the autocorrelation at lag 3, and it's not 0. Therefore, it's not white noise. Is that true?
Yes.
Not necessarily, right?
Yes.
I thought I know it's always needed to be.
Okay, that's what I said, right? Okay, but so I take a sample and I measure the autocorrelation function at lag 3 or at lag 5, just one lag at lag 5, and it's not 0. Does that mean that series is not white noise? No. It doesn't mean. I have to test the hypothesis because the fact that I have observed it and it's not 0, it could be statistically 0. But what I'm observing is not 0. And that's why when you test hypothesis, you say at the 95% confident. It may not be exactly 0, but I am 95% confident that it's around 0, such that it doesn't lie far away from 0. You remember that? That's why you test hypothesis, yes?
Yes.
Okay, and that's why, Danny, you said we build confidence interval because if I come in and say, look, the autocorrelation at every lag must be 0, and I take autocorrelation at 1 lag and it's not 0, just 1 lag, it's not 0, but if I test hypothesis, it can maybe within 95% confidence, it's around 0, enough for us to say, okay, even though the number we are looking at is not 0, but at 95% confidence, I can say it's 0 because it's not too far away from 0. And that's why you take confidence level of significance 5% or 95% confidence. That's what you did in statistics. I'm just saying it a different way. Is that right? Okay, good. Excellent. Okay. Whew. So if I take a sample of a time series and I measure the autocorrelation at different lags, but I look at autocorrelation at a particular lag, it's not 0. If even if it's not zero at all the lags up to like 12 or up to like 24, that series could still be white noise because those numbers that are not zero statistically could not be significantly different from zero. Remember, when you reject a null hypothesis, when you fail to reject a null hypothesis or crude, if I say it in a crude way, if you accept the null hypothesis, what are you saying? That even though the numbers are different from zero or from your null hypothesis, but they are not statistically significantly zero. They are not statistically significantly different from zero or from your null hypothesis. You studied all of this in statistics. Maybe I'm not saying it the right way that you know. But when you say reject the null at 5% level of significance, what does it really mean in English? I reject the null at 5% level of significance. Let me use the Baruch College students. The null hypothesis is Baruch College students are on average 5 feet tall. So I take one particular sample and I measure the average height of Baruch students in that sample of 30. And that average for that particular sample is 5 feet 6 inches. That doesn't mean that that Baruch College students don't have average height of 5 feet, even though the average height in this particular sample is 5 feet 6 inches. So I test the null test hypothesis, and then I calculate my Z statistic, and then I compare my Z statistic to what the Z will be if Baruch College students are 5 feet. If Baruch College students are 5 feet tall, then the Z from my sample should be within a range. If it goes outside of that range, then Baruch College, then I reject the null. But if my Z or my T is within that range, then I say Baruch College students are 5 feet because I have failed to reject the null hypothesis. So therefore, I have failed to reject that the observation is statistically different from zero. That's what we mean. The same thing with when we want to test for white noise. I can give you a series and you test, and you go ahead and you test for whether the autocorrelation at each lag is zero. But the autocorrelation from that sample at different lags is not zero. Maybe it's 0.12 here, is 1 here, it's 0.1. The correlation is plus 0.12 here, is plus 0.3 here, is plus 0.25 here, is negative 0.07 here. Those numbers are not equal to zero. But they are not statistically far removed from zero enough that we say, oh no, this is not a white noise. Even though each of those numbers are different lags, it's not zero, but it is a white noise process because each of those numbers is not too far removed from zero. How far is too far? That's why we do 95%, 90%, 5% level of significance, 10% level of significance. So anything that lies within that range, within that range, plus or minus, within that confidence interval range, it is still zero. Even though the particular numbers are not zero, but they lie within a particular, plus or minus confidence band. Remember, Danny, you mentioned confidence interval? Oh, I'm sorry, Andrew. I keep saying Danny. Sorry, Andrew. So you build a how do I say, a band, plus or minus. That's what confidence interval is, right? Plus or minus. If it's plus or minus 1 standard deviation, 95% is plus or minus 2 standard deviations. So as long as our numbers fall plus or minus 2 standard deviations within, with around 0, we say it's a white noise, even though at each lag we're not pure. the fact that we define a white noise process to be that one, the first condition is true, the second condition is true, but then we look at the autocorrelations at each lag, maybe up to lag 12, and they're not, each of them is not 0. Okay, that doesn't mean it's not a white noise. If each of them is 0, 0, 0, 0, 0, 0, 0, 0 up to lag 12, then definitely it's a white noise. But in real life, you cannot see a time series with autocorrelation at every single lag 0. No. Okay.
Professor.
Yeah.
So if I had, let's say hypothetically, I had a time series of 3 lags. So let's say lag 0 was 1, lag 1 was 0, lag 2 was -1, and lag 3 was 1. Would that be an example of a white noise process?
You have to, no, the answer would be you have to test for hypothesis. See, why I don't like the timing of this class is before I even begin to explain something, the class is almost over. All right, but let me show you what I'm talking about. Okay, let me show you what I'm talking about. So I'm going to bring up your textbook now. And look, all of you, in this class, we're not doing more than 4 or 5 chapters of the book. We have, and chapter 3 is all exercises. So chapter 3 doesn't really teach us. In chapter 3, we kind of use it's kind of projects in chapter 3 of your textbook. So the author has gone and used real life data to verify many of the concepts that your textbook teaches you in chapters 1 and 2. So really in this class, we have 3 or 4 chapters to study. So we have time, okay? My experience is in the past, when I have finished this class, students are still a little shaky about some concepts. I don't want that to happen this semester. So we have time. I'm going to give it enough time to explain many of these concepts. I feel frustrated tonight that this class, it's already 7 p.m. and I haven't really started talking or showing you things, but that's okay, all right? I want you to understand it properly, but the way for you to understand what we're doing in time series analysis is I want to bring in your knowledge of statistics, what you already studied in statistics.
Professor,
So
I have a question, Professor.
Andrew, yes.
So when you say that mean is constant, you just mean that we're not adding to the time series?
No, meaning the average is
yeah,
constant.
the average is constant. That means in lag 1, lag 2, lag 3, the mean is constant. So is that saying that we're not adding to the time series?
I'm not discussing anything about lags now.
No, I'm just curious because I was trying to understand what I was going over all the necessary requirements for it, and I was thinking
okay. So let me give you an example. Okay, if you go out there and you take the S&P 500 returns, okay, from let's say from the year 1920 to the year 2000. Yeah, let's say you have month by month returns. Are you with me?
Yeah.
And you calculate the average. In other words, add up all those returns, divide by the number of months. It's a number. And then you okay, that's fine. And then you go out and take S&P 500, the same S&P 500 from 2000 to from 1950 to 2020, something like that. You measure the average. Okay. What we're saying is for a stationary time series, the average shouldn't change. But if you make those two periods that I mentioned, from 1920 to year 2000, and then from 1950 to year 2000, even though there are different ranges, let's say we keep the ranges constant or even different. If we measure the average numbers, okay, from 1920 to year 2000, what, 80 years of monthly data. If you begin in 1950 and you take 80 years of monthly data and you measure the average, those two numbers, chances are they'll be different numbers. Is that correct?
Yeah.
Okay. The fact they are different doesn't mean that the process is not stationary. The returns of the S&P 500 does not come from a stationary process. The number, this one could be 5%, this one could be 5.7%. The fact that those two numbers are different for those two samples doesn't mean that statistically that the average of the distribution is zero, is changing. It does not mean that. That's why we build confidence intervals. As long as we take any sample of return and measure the average, and the average lies between 4.9 and 5.5, we can say that the real average of S&P 500 returns is 5%. But every sample we take doesn't have to be average 5%. Okay, are you with me?
Yeah, that was my question, because I was thinking like there's no way that every lag, like they're going to be the same value, and the only way for it to be constant is if they're the same value.
But
that
that's
makes
why
more
you
sense. Yeah.
But that's why you build confidence intervals from statistics. If we say the average return for S&P 500 is that S&P 500 time series is stationary, the average return is 5%. It doesn't mean that every sample of, every period of returns of S&P, this 20 years, it doesn't mean that each time we take a sample that the average will be 5%. No.
Thank you. And it makes
But
sense.
if you take many samples and the average of those samples lie within plus or minus 2 standard deviations, are you with me? Then we say, okay, statistically, it's 5%, even though each average we measure is different from 5%. That is statistics. That is confidence interval, and that is test of hypothesis. The same thing for white noise process. Okay, if I give you a series and you measure the autocorrelation at different lags, those numbers representing the autocorrelation, those numbers could be not zero, minus, plus, minus, plus, minus, plus. Not zero, but as long as they lie within this particular range, we can say at 95%, we can say with 95% confidence that they are zero, as long as they lie within a certain range. Okay, that's what hypothesis testing does for us. That's what confidence interval does for us. Okay, guys? All right, let me just show one thing and then we stop class and then I'll continue next time, okay? Give me a second. Where's my textbook? I have my textbook here. All right. How many minutes do I have? I have, wait, the time is gone already, right? So just give me 1 second. Let me show you something, okay? And then I'll continue. I shall continue on Thursday. Okay. Are you guys looking at this page? Okay, awesome. Oh my God, you suck, Anache, you suck. All right. Just bear with me, and I want to. Okay, are you looking at this graph here, right?
Yes.
Okay, so look, so on the y-axis here, I plot the autocorrelations. Okay, what numbers can autocorrelations take? What numbers? Anybody tell me quick?
-1 and 1.
Yeah.
from -1 to 1, okay? From -1 to positive. And these are the lags on the horizontal axis, okay? And look at these dashed lines, the broken lines, okay? What are these broken lines? They are the confidence interval.
Confidence interval.
You see? So they are the confidence interval. So it is possible. So look at this one, lag 0. At lag 0, what is my autocorrelation is +1, right? Is that right?
Yes.
Right.
Okay, so this is +1. So that condition is satisfied. At lag 0, the autocorrelation is +1. But look, at lag 1, the autocorrelation is not +1. At lag 10, 11, 12, let's call this lag 12, the autocorrelation is positive and beyond. Okay, so look, so if you go through here, these autocorrelation numbers, they are not exactly 0. Some of them are, like this one here is negative, this one is negative, this one is negative. Okay, this one is, I'm sorry, this one is positive, this one is negative. So they are not 0. But guys, pay attention, please. You see this one here. This one lies beyond the interval. This one lies beyond the interval. Suppose this one here, it's not 0, but it's within this interval, right? Within this broken line. And this one is inside of the broken line. As long as at lag 0 is +1, then at different lags, they are each of them not 0, but they all lie within the 95% interval. If they all lie within the 95% interval, but they are not 0, then statistically, at 95% confident, we can say they are 0. And therefore, this is a white noise. But because these two are not in the interval, this one is not in the interval, then I begin to suspect that this is not a white noise process. It can still be a white noise process, especially if we are dealing with 24 lags, and out of the 24 lags, only these two break through the interval. It doesn't mean that it's still not a white noise, okay? So on Thursday, I will show you statistical tests that we use to determine, even though the numbers are not 0 at each lag, but it could still be a white noise process. Finally, the fact that we define a white noise process to have autocorrelations at different lags, not 0, but at different non-zero lags to be 0. The white noise definition says the autocorrelation should be 0 at different lags. The fact they are not 0, still that process can be white noise as long as the autocorrelations at each of those lags lie between those intervals. Are you with me so far? Okay, good. So on Thursday, I'll bring an example and then continue. Let me stop recording now.
The recording has stopped.
Okay, guys, so basically what I explained tonight is your knowledge of statistics. I review statistics, confidence interval, and hypothesis testing, because we shall use those concepts. My friend Lily and Roxolina and Andrew and Danny. So what I'm trying to explain, and everyone else, what I'm trying to explain, that we can have a white noise if we're looking at 24 lags. We can have a white noise if the autocorrelation at each of those lags from lag 1 to lag 24, each autocorrelation may not be 0. But as long as they all lie within that confidence band, then we can say statistically they are not different from 0. So that process is a white noise because all those conditions, 1, 2, and 3 are satisfied. Okay, guys?
Okay.
Okay.
Sounds good,
All right.
Professor. See you next class.
So see you next class. Okay, we'll finish up this and do some R work next class. Bye, guys.